1.2. Translate the following expression into prefix form. We could have just okay, wait. Exercise 1.2 dot scheme, and then okay. So yeah, I think the top is so it's a fraction, right? So the first expression, the first operation we do is dividing. Then it seems to be, how do we do that? It's a sum of a bunch of things, right? So I think it's going to be like that. Minus 2 minus 3 plus 6 divide 5 4. I think that is my solution. Exercise 1.3. Define a procedure that takes 3 numbers as arguments and returns the sum of the squares of the 2 larger numbers. Okay. Exercise 1.3 scheme. Okay, let's just call it F for 3 numbers, so A, B, C, and returns the sum of the squares of the 2 larger numbers. How do we get the 2 larger? I mean, we can start using lists and stuff, but we don't have that yet, right? So, cond. I mean, I could, okay, let's just try something. How do you write that? If, wait, so this is to denote the list, and this is like the first pair. This is the first, what is it called? Predicate of the pair, of the first pair. So if A is smaller than B and B is smaller than C, then we know that A and B are the smallest. Wait, define a procedure that takes 3 numbers as arguments and returns the sum of the squares of the 2 larger numbers. So I think we should first define sum of squares. It does plus A times A and B times B. Okay. And now in this case, we know B and C are the larger, right? So then we do sum of squares of B and C. Okay, so we could write it that way, right? I mean, if I knew, like, if I'm allowed to use all features of the scheme, I would probably like sort the list and take the first 2 elements, right? But I guess we can just write 3 cases or something. If A is smaller than C and C is smaller than B, then we do oh, that's the same. What? How do you get the 2? Man, I feel really dumb right now. 3 numbers and returns the sum of the squares of the 2 larger numbers. But how do we get? So we need to define a case for each, where we always check, like, if A is the smallest, then we do sum of squares of the other 2, I think. So if A is smaller than B and A is smaller than C, then A is the smallest, right? And then we exclude A. So, okay. No, wait. So if B is smaller than A and B is smaller than C, then B is the smallest, so we need to do A and C. And then if C is smaller than A and C is smaller than B, then we do AB. Like that. I think that might be okay. Let's try that. Eval buffer. Oh yeah, I have a shortcut for that. Let's try it. So f of 1, 2, 3. What should that be? Then it should return 4 plus 9, which is 13. Fuck. Oh, excuse my language. Why did it not put the buffer down here? F. What? Okay, let me try and boot up Geyser again. I don't know what the fuck that is. Okay. Geyser. And let's try f of 1, 2, 3. What? Okay. I don't know what that is. 1, 3. Wrong type to apply, it said, right? Oh, wait, we need Geyser here. Okay. Wrong type to apply. What? Okay, let's try doing backtrace. I've never done these. Nothing to debug. Oh, okay, because it's not running anymore. I mean, it's not in the backtrace mode or something. Backtrace. What? Let's try just doing sum of. Does this have auto completion? Yes. Sum of squares of 2 and 3. That works. So there's something wrong with the way my cond expression works. I think maybe we don't need to put it inside of a list, the pairs. It's just like that. Let's see if that works. Okay. F of 1, 2, 3. Boom. Okay, that works. So let's try. Okay. So if we permute the 3 arguments, it should always return 13, right? So I think we can test it that way. F of 3, 1, 2. Yeah, so it seems to work. Exercise 1.4. Observe that our model of evaluation allows for combinations whose operators are compound expressions. Use this observation to describe the behavior of the following procedure. Okay. So what we saw like 2 models, right? We saw substitution and normal form or something. Let's go back. Let's see. Okay, well, that is further than we were. Here. Applicative order versus normal order. According to the description of evaluation, first operator, then operands. So, okay, so I'm going to assume they're asking applicative order. So if we evaluate everything and let's see. Observe that our model of evaluation allows for combinations whose operators are compound expressions. Use this observation to describe the behavior of the following procedure. Ah, okay, now I get what he means. So here is an expression that returns a function, and then it applies the function that was returned by this thing. Okay. Exercise 1-4. Let's do it in org mode because we need to add some stuff. Okay. Function definition. So we can look back at it. Evaluation. Wait, what? Use the observation to describe the behavior of the following procedure. But okay, when we, what does it mean? Describe? It's just in words. I'll just describe it in words. A plus abs b is defined as or yeah, how do you write that in English? If b is a positive number, then a plus b is defined as the sum of a and b. If b is a negative number, then a plus abs b is defined as the difference of a and b. Like this. I think he just wants us to think about the fact that the operator, I think, can itself be something that is computed. I think that's the point of the exercise. Exercise 1.5. Ben Diddle has invented a test to determine whether the interpreter he is faced with is using applicative order or normal order. He defines the following two procedures. Define PP. Define test xy. If x is equal to 0, then 0. Otherwise y. Then he evaluates the expression test 0p. What behavior will Ben observe with an interpreter that uses applicative order evaluation? What behavior will be observed with an interpreter that uses normal order evaluation? Explain your answer. Assume that the evaluation rule for the special form if is the same whether the interpreter is using normal or applicative order. What? Explain? Well, okay. Assume that the evaluation rule for the special form if is the same whether the interpreter is using... Huh? I don't really understand this part. Oh, he explains it now. The predicate expression is evaluated first, and the result determines whether to evaluate the consequent or alternative expressions. Okay, so I would have assumed that in normal order, okay. No, never mind. Okay, let's try and work this out. Exercise 1-4. What? Wait. Exercise 1-5. Okay, 1-5. Okay. Let's put everything in here. Definitions. Okay. Or let's write it as a program. And then here we can write normal, or let's first do applicative order evaluation. Test 0p. Okay, let's see here. So first we want to evaluate the value of evaluating what? P, okay. And P is like an infinite loop. seems like. So if this is applicative order, this is just gonna get stuck in the loop, right? I see what he wants to try now, I think. Test if x is 0, then 0. Okay, so in one of the two cases, it's gonna get like short-circuited, and in the other, it is gonna be stuck in a loop because it evaluates the, it tries to evaluate the body of the if statement or something like that. Wait, I have to think about this. If the first argument is 0, then return 0. Otherwise, return y. But here he says the evaluation rule is the same. The predicate expression is evaluated first, and the result determines whether to evaluate the consequent or alternative expression. Huh? Strange. Let's see here. How much? Okay, we have some more time. This test. Okay, so I think what's going to happen in the applicative order is it's going to just short circuit. I mean, it's not, maybe short circuit is not the right word, but this is just going to return 0. Return 0. Or let's write it like this. Gets stuck in loop because it evaluates P. I think that's what's going to happen. Let's actually try. So they said that in practice it uses applicative order, right? So let's see here. So P is defined as a loop, I think. And then let's try typing that. Test is defined as if x is 0, then 0, otherwise y. And then we do test 0 P. So this, if we're right, this is just going to return 0. Oh, it gets stuck in a loop. Huh? So we were wrong. So I switched the two around. Or this thing uses normal order. I don't know. Okay, let's write a little section. Trying my hypothesis in practice. The REPL gets stuck in a loop. So either, okay. So either my hypothesis is wrong, or the REPL uses applicative order, or the REPL uses normal order. Okay, that's interesting. I really... Let's go, or should we continue? I can just look up the answer to this exercise, maybe. And then we continue. Wait, I'm gonna see if there's more exercises. Okay, yeah. Let's just continue reading. We have only 5 minutes left, so maybe we can read 117. Chapter 1.1.7. Section, not chapter. Example, square roots by Newton's method. Procedures, as introduced above, are much like ordinary mathematical functions. They specify a value that is determined by one or more parameters, but there is an important difference between mathematical functions and computer procedures. Procedures must be effective. As a case in point, consider the problem of computing square roots. We can define the square root function as square root of x, the y such that y greater than or equal to 0, and y squared is x. This describes a perfectly legitimate mathematical function. We could use it to recognize whether one number is the square root of another, or to derive facts about square roots in general. On the other hand, the definition does not describe a procedure. Indeed, it tells us almost nothing about how to actually find the square root of a given number. It will not help matters to rephrase this definition as pseudo-Lisp. This only begs the question. The contrast between function and procedure is a reflection of the general distinction between describing properties of things and describing how to do things, or as it is sometimes referred to, the distinction between declarative knowledge and imperative knowledge. In mathematics, we are usually concerned with declarative, what is descriptions, whereas in computer science, we are usually concerned with imperative, how to descriptions. How does one compute square roots? The most common way is to use Newton's method of successive approximations, which says that whenever we have a guess y for the value of the square root of a number x, we can perform a simple manipulation to get a better guess, one closer to the actual square root, by averaging y with x over y. What? Okay. Square root by averaging y and x over y. For example, we can compute the square root of 2 as follows. Suppose our initial guess is 1. Okay. Why does that work though? Continuing this process, we obtain better and better approximations to the square root. Now let's formalize the process in terms of procedures. We start, it's like the, no, I don't know. Now let's formalize the process in terms of procedures. We start with a value for the radicand, the number whose square root we are trying to compute, and a value for the guess. If the guess is good enough for our purposes, we are done. If not, we must repeat the process with an improved guess. We write this basic strategy as a procedure. Define square root iter, guess x if good enough, guess, square root iter, improve guess. A guess is improved by averaging it with the quotient of the radicand and the old guess, where define average xy, divide, okay, yeah. So this just, okay. We also have to say what we mean by good enough. The following will do for the illustration, but it is not really a good test. So there, okay. So if the difference is less than 1,000th, then it's good enough, okay. The idea is to improve the answer until it is close enough so that the square differs from the radicand by less than a predetermined tolerance. Here, 1/1000th. Finally, we need a way to get started. For instance, we can always guess that the square root of any number is 1. Define square root of x square root iter 1. If we type these definitions into the interpreter, we can use square root just as we can use any procedure. I wonder, maybe it's already built in. Yeah, it's already built into Guile. But okay, they're just illustrating a point here. The square root program also, can you just redefine stuff? I don't know. No. Okay. How do we? So I really wonder in in Emacs, can you tell Emacs to, like, if you just run a command to do it, to put the result into a specific buffer, or a specific window, because for me it just picks like random windows, and then I don't understand why. Okay. Oh my god, struggling. Hello. Okay. So now we can say what is size. Okay. Are we gonna, okay, let's type everything in here. Boom, boom, boom. Up, and then we throw away this explanation. Okay, and now we try and evaluate the buffer, and that seemed to work. Square root of 3. Huh, but okay, so I think it did not overwrite our definition, right? Let's try and calling this square root 2. No, prime. Can you do that? Let's call it that. And now we go down here, square root SICP 3. Huh? Whoa. Okay. Let's try quitting out of here. And then bring it back. And then square root. Okay, so the SICP version is not defined. Then we try square root of 3. Ah, yeah, so it is different. Okay, so after 1/1000, it goes off the rails. Okay, and so you can redefine functions is what I was trying to test. Okay, and we're over 25 minutes, so I'm gonna end it here.